All right, so welcome. I posted, the video got a little bit long, I think. I can't quite remember, but it was a little bit longer than our 50 minutes, but hopefully you were able to get through it. And today I want to talk about expectations. So expectation values or expected values you've probably seen before. As well as maybe you've seen the variance of X. We're going to talk about it a little bit more and just different expectation values. Usually we end up calling them expected values, but they're, I mean, technically they're expectation values. So you have an assignment due tonight. If you find that, you've had quite a bit of time to work on it, so hopefully you don't need an extension for this one. A little bit hesitant to do an extension for this one, but later, if it gets to be too much with your other courses, then just let me know and I can make adjustments on my end. So, but this one I'd like to keep it for tonight, and so. Assignment, assignment number 1. I couldn't decide what to call it. We've had like kind of lab things and assignment things. Usually what I end up doing is I do whatever makes your grade the highest. So if there's something that's like an assignment or a lab, I might shift it around to distribute the weight higher on something that's worth more. So an assignment number 1 is due tonight at 11:59. Okay. So those are those questions from the textbook, and you have chapter 1 that I posted, so you can use that. Okay, so section 1.8 is on the expectation of a random variable. Okay, so if we have a random variable X, then the expected value, or the expectation value, as we'll start calling it, is the mean of X. We've probably seen that at some point already, but here we have it. So given a random variable X, we define the expected, or rather the expectation value of any function g of x, as a weighted average of the possible values of g of x. Okay, so as a weighted average, as a weighted average of the possible values of g of x. Weighted by their probabilities. Weighted by their probabilities. We've seen that before, probably, right? If you have a probability distribution and you've got some output X, each with some probability of happening, then we can, so that's for a discrete situation, right? Then we can multiply those through and we can find the expected value, right? Or the expectation value. So we can say that if x is a discrete random variable, with PMF denoted by P of x, then what we can say is that the expected value of G of x is the sum over x of G of x times P of x. Yeah. That's probably something that we've seen before, right? Especially if you remember the expected value of x is the sum over the x's of x times P of x. Right, we've probably seen that before, but now instead of just looking at x, which translates to x here, we're looking in the general sense of G of x. So G of x times P of x is the sum now. Okay. One thing that we probably didn't make mention of before because we weren't considering situations where it would happen, but this only happens if the expectation doesn't diverge. Okay, and so I don't know why I stumbled through that, but this is only true if the sum over x of the absolute value of G of x times P of x is less than infinity. Okay. So here, let's see if I can find, I'll do maybe dark green here. So that is to say that if the expected value of the absolute value of G of x, all those brackets, right? You want to keep track of those brackets, G of x, inside absolute brackets, inside brackets of the E of x. So if the expectation of the absolute value of G of x diverges, right? Meaning that it goes to infinity, right? We say the expectation value does not exist. Right? And I'm just, this blue one keeps catching my eye. I should probably explain what I was doing here in case you're looking back and you're kind of, we have already seen, or we have seen this, right? E of x. But notice the similarities here. We're just replacing x with a general G of x. So if the expected value of the absolute value diverges, so it is not less than infinity, then we say that this expectation doesn't exist. Okay, so that can happen, and that's going to be a concern for us. So of course we can talk about the discrete situation, so that's the sum, or we have a continuous situation where we're going to be looking at the integral. So if, just to, if x is a continuous random variable with PDF f of x, so same setup here, just looking at discrete versus continuous random variables. So if we have a continuous random variable with some PDF f of x, then we can say the same thing again. The expected value of G of x is the integral over the set of real numbers, negative infinity to infinity of G of x times f of x with respect to x. If the integral from negative infinity to infinity of the absolute value of G of x, oops, make it, whoa, what happened here? There, I don't know what happened there. the absolute value of g of x times f of x with respect to x has to be less than infinity again, okay? This is for the same reason. In fact, this integral is the expected value of the absolute value of g of x, right? And so we have the same situation in either scenario. Okay, so the same description applies. Okay. So first thing I want to do is show you a situation where it does not apply. I also want you to kind of not get too bogged down with what we're doing here, because I'm going to show you how to use Desmos to kind of confirm these things. Okay, and so I have Desmos here, but if you don't have it, then it might be worthwhile Desmos is a free app, and the app looks like it's got this like curvy kind of squiggly graph and then x squared or some x to the power of some even function here. So if you open Desmos, I have these mapped out. So I do want to talk about how do we use Desmos to confirm these things, because I find that that's really helpful for me when I'm working through these things. So we will have a look at this, and I'll show you how to use Desmos for some of these things, at least. So when I work through these things, I always feel uncertain, right? I'm working through these things. I'm not sure if I'm doing it right. And it's not until you've done a ton and a ton and a ton of them that you start feeling more comfortable, right, with the steps that you're taking. And so I always find that it's nice to have something where I can check to make sure that I'm on the right track, right? And so that's what I want to give to you using Desmos. So, and it's a free app, and you can download it and you can use it. In fact, I encourage you to use it for a lot of this stuff. Sometimes it's hard to use it if you don't know what you're looking for, though, right? So what I wanted to do was introduce kind of a weird distribution. It looks like the normal distribution, but it's got some special properties, like it doesn't have a mean, for example, and it's the Cauchy distribution. So there are many, many, many different distributions depending on what you're trying to describe. We're familiar with the normal distribution, right? And so we can talk about the normal distribution, but the Cauchy distribution is a different distribution with a similar shape. So that's confusing, but here we go. So to see an example of what can go wrong, consider the Cauchy distribution. Consider the Cauchy distribution, and this should HY distribution with f of x. I'll put it on a fresh page here. F of x is 1 over pi times 1 over 1 plus x squared. You could combine these, but what's nice about having the constant outside, or 1 over pi, is just a constant, right? Is that you can extract it and you can pull it outside the integral, right? And so that's a nice thing. So that's why I write them separately. You could combine them if you want to, but I wouldn't. Okay. So some of the things that we could look at is that, okay, well, the total area under the curve is still 1, right, for this distribution. And so how would we check that? Well, we could integrate this whole function from negative infinity to positive infinity and find that it equals 1. Okay. How we would do that, we would use a trig substitution. We're not going to go into it, but I will make a note here in case you wanted to try it, right? And so we could use a trig substitution that x equals tan theta to show that the sum, the integral from negative infinity to infinity of f of x dx is 1. What does that mean? It means the total area under the curve is 1. Right, and that's true. Total area under the curve is 1. That's what we can confirm there. And so you could go through and you could do it, but we're gonna leave that alone. So what could we do? Well, I could do this. Let's see here. I think that's the first thing that I did. Now, what I'm going to do here is I'm going to screenshot this so we can bring it into the notes. I also want to show you how to enter these, but I just want to screenshot them before I lose them. And how do I screenshot again? Oh yeah, like that. Okay. Save it there. Okay. And so here, I want to make this a little bit bigger. We can also confirm this using Desmos. Okay. And here, as a little note, it's a free app or a free graphing. It does more than graph, but it's a free graphing app that I would encourage you to check out, especially if it helps you to see these things kind of on a graph like this. So just to kind of show you around in case you're unfamiliar with Desmos, so the little kind of graphy looking thing here, that tells me that, okay, it was able to just graph, right? And that graph is shown in red. It's the only one that I have on here. And so when we look at this, right, this looks like a somewhat normal distribution. It looks like it follows a normal distribution. I would kind of start to want, it looks a little bit flat here, but that can happen in a normal distribution as well, right? So there's nothing about just looking at the shape that makes us say, oh, that's a Cauchy distribution. No, it's how we define the shape that makes it a Cauchy distribution. Okay, so it looks like a normal distribution, okay? And what we can do is we can ask Desmos to integrate it from negative infinity to positive infinity. And what have I done here? Well, I've just taken the PDF, right? Because I'm just integrating the PDF over the set of X. And so, or with respect to X. So, and then I find that the integral there is 1, okay? When I look at the same thing, but when I multiply by the absolute value of X here, then all of a sudden it becomes undefined. What am I calculating here? This is actually the expected value of the absolute value of X, which is some function of g of X. In fact, it's the simplest version of g of X. So here, this is the expected value, and maybe, well, I didn't really have any more room here. That's the expected value of the absolute value of x, right? And so that's one of those things that it has to be less than infinity, right? So it has to be defined. But in this case, they're saying, no. And we're going to have a look and see kind of where that comes from. But if you're feeling like me, a little bit rusty on this stuff, then it's nice to have a fallback plan on, okay, why was it undefined again, right? And so, or was it undefined rather? And then I've got this one, we'll look at that one later. Okay, so what I want to do first is I just want to show you how to enter this integral, and then you could manipulate it to make this next integral, right? It's hard to get these infinity. In fact, you have to type in infinity, so that can be a little bit weird. But what I want to do is I just want to show you how to do that first integral. Okay. This is usually the keyboard you start with. And so what you're going to want to do is we're going to insert a function. So a function, and of course you could use Maple, but it's hard to have access to Maple all the time. So that's why I prefer to introduce something like Desmos. But of course, if you like to use Maple, you can just use Maple. Okay. The integral. So I found the integral, it's in, usually it defaults to the trig section, but the integrals and the summations and the products are all in the MISC section. And so if you hit that integral, I guess could have done a double integral, no. Then it wants to know the lower bound, I guess. And so the negatives is just going to be from a minus. And so, and then you go to the ABCs and you type in infinity, which I feel like infinity. Oops. Infinity. Hey, it's not keeping up here. It's not using my, it's not catching my pen. So let me see here. I'll use my finger. There. As soon as I type infinity, it'll just change it to the infinity symbol. And that's how you know that it's caught on to what you said. So I'm going to use my finger because it didn't like my pen so much. There. So if I want to find just the integral over the Cauchy PDF, well, that's going to be, and I like to use brackets. As long as you're careful, it'll show you how it's interpreting what you said. And so just make sure you use lots of brackets. They don't hurt, right? 1 divided by, and then pi is actually on that first pad on in the bottom right. So 1 over pi, and then I jump up and I close those brackets. And especially if you've worked in Maple before, you know how picky it can be with, oh yeah, I just put a bracket down here. It doesn't make sense. So then you have to kind of jump up and show it what you want. I don't think you need to have the multiplier in there, but it doesn't hurt, right? And then I want 1 divided by 1 plus x squared. Close that bracket. And then I'm just going to type in dx. So dx. And notice that it just evaluates the function there. Okay. And you could change the bounds. You could change anything, anything you want. Right, but just make sure that it looks like the function that you're trying to evaluate, because if it's typed in incorrectly, then it's just going to do what you tell it to do. So here, I'm going to say to get infinity in Desmos, type infinity, and it will automatically change to infinity. So here I want to talk about maybe one of these here. So pretty cool, pretty fun, and so fun. In fact, I forgot what we were going to do. Oh yeah, so we could show that the total area under the curve is still 1, and so that's one of the properties of a PDF, and so that's good, that's fair. But just because it's a PDF doesn't mean that it's going to have an expectation value. And so, however, the expectation value E of X does not exist for the Cauchy distribution. Okay. So we've seen it already, right? If we take the integral from the absolute value of X, for example, and then multiply it by the PDF, which is f of X dx, then we get an undefined result. So how do we get there, right? Maybe a little bit rusty, but at least we know that, okay, it's going to be undefined. How? So what we can do, I'm going to start on a fresh page here. Or maybe I'll say, consider the expected value of the absolute value of X, which is the integral from -infinity to, oops, that didn't look like infinity. Sometimes I feel like I need an infinity stamp, right? All my infinities look lopsided. The absolute value of X times f of X with respect to X. So what we can do is, well, we can replace the f of X with the actual PDF for the Cauchy distribution. Okay, so let's start there. -infinity to infinity of, and the absolute value of X times 1 over pi times 1 over 1 plus X squared dx. So what I'm going to do is I'm going to shift this 1 over pi, and that's why we kept this constant just kind of on its own, because then I know I can move it outside of the integral and it doesn't change anything. And so this becomes 1 over pi times the integral of negative infinity to infinity of the absolute value of X over 1 plus X squared dx. What could we do here? With the absolute value, it kind of makes a mess. And so what could we do? Well, the absolute value of X looks like this, right? And if I'm looking at -infinity to positive infinity, what if I just consider half of it, right? So imagine kind of going down the y-axis. What if I just consider the positive half of it and multiply it by 2, right? And replicate it across the other side. Okay, so here I'm going to make a note. We can consider only positive values of X. And then just multiply by 2. And then multiply by 2. Okay. So what we get then is we get 1 over pi times 2. Okay, so I'm going to highlight that because that's new. And then instead of going from negative infinity to infinity, what if I just go from 0 to infinity? Because then I can ditch the absolute value brackets, right? I'm only considering half of that situation, I guess. So from 0 to infinity of x over 1 plus x squared dx. If I have to evaluate this integral, what would I do? I would probably have to use a u substitution. In fact, that's what I'm going to do. And so here, we evaluate this using a u substitution. Yeah. Where I'm going to let u be 1 plus x squared, which means du is 2x dx. If I let u be 1 plus x squared, then what I have left is x dx, right, which I see here. And so that's what helped me choose my u. Right, and so then what if I write du over 2? Well, that can take the place of x dx. So then du over 2 is the same as x dx. So now what I have is I can take, so the integral, back to the integral then, becomes 2 over pi times the integral from 0 to infinity of 1 over u times du over 2, right? Replacing those 1 plus x squared. So that becomes, so I've split up and kind of pushed the x over to the side. And so I have 1 over 1 plus x squared, but I'm replacing 1 plus x squared with u. And then I'm replacing x dx with du over 2, right? And so that's what's going on here. So then I have du over 2, or 1/2 times du. That 1/2, either way, I can shift it to the outside of the integral because it's just a constant. And so I have 2 over pi times 1 over 2 integral 0 to infinity of 1 over u du. This means that 2 over 2 cancels out, so they disappear. And then I have the integral of 1 over u du, which we know is the log of the absolute value of u. Okay. But I'm going to re-substitute u equals 1 plus x squared. And so then I get, wait, I'll zoom in here. So then what I end up with is 1 over pi, right, because those 2's canceled, times the log, the natural log of the absolute value of 1 plus x squared, evaluated over 0 to infinity. I don't need those absolute values, but whatever, doesn't hurt. So what we can do is, really what we're doing is, we can't, infinity is not a number, so you can't really plug it in, right? Like we would if we had bounds a and b, for example, right? But we can take the limit as x goes to infinity, right? And so what we'll say is, or rather, the limit as r goes to infinity, just kind of some placeholder. You could use a, b, but we use those for endpoints. And so I don't know, I just stole this from somewhere. R goes to infinity of 1 over pi, and they used r, so why not? I thought, why not? 1 over pi times the log of 1 plus x squared from 0 to r. Now, the log of 1 is 0. You can plug in 0 here. So I can focus on this one first because it just goes away, right? And so if I have 1 plus 0 squared, that's 1. The log of 1 is 0. 0 divided by pi is still 0. So in the end, I'm going to end up subtracting 0. But that's the reason that I'm just ignoring it, is because I'm going to focus on when r goes to infinity. And so here, this becomes the limit as r goes to infinity of 1 over pi times the log of 1 plus r squared. And that puts us at infinity. This matches the result we found in Desmos, which was undefined. Okay. So you could do that to check it. That seems like a lot of work, or really just knowing that you have to check that the absolute value of x, the expectation of the absolute value of x can't be undefined, right? That's a good first step, and you can use Desmos to do that. Okay. Now let's consider an example where it actually does work out, and that's going to be more common, right? And so to give an example, where things work out, consider the uniform distribution. Which is, if we think about some f of x, it's going to be 1/2 if x is between -1 and 1. Notice not inclusive of -1 or 1, that doesn't matter. Then we can find, for example, the expected value of x squared is what? Going back to that other situation, the expected value of, and then whatever's inside is that thing that's inside times the PDF dx, right? And so in this case, it's going to be -1 to 1 of x squared times f of x dx, right? So just to highlight here, if I want x squared, and then that x squared is going to be there times f of x dx. So if I want to evaluate this, then this becomes, remembering that f of x is 1/2, so this is really the integral from -1 to 1 of x squared over 2 dx. And if I evaluate this, right, it becomes x to the 3/3 times 2, which is x to the 3/6 from -1 to 1. If I evaluate this, then I get 1 to the power of 3/6 minus -1 to the power of 3. Remember, when you take something to the power of a negative to the power of 3, it retains that negative, right? So then I have 1 plus 1/6, which is 2/6, which of course reduces to 1/3, which we saw here, which I can show you in our Desmos output here. Copy. Right, 0.33333, 1/3. So you can do it in Desmos, or you can do it by hand. And Desmos will definitely just warn you if you're trying to find something that's actually undefined, right? It'll just say undefined. So, okay. Let's see here. One thing that's really nice, a nice property about expectation values or expected values, is that because we're dealing with sums and integrals, those calculations are going to be linear. And so note, that because the expectation value is defined using a sum or an integral, depending on the situation that you have, discrete or continuous data or random variable, is defined using a sum or integral. It is a linear operation. Meaning what? If I have some generic expectation value, so the expected value, and you know what, I'm going to use big square brackets here, of K1 G1 of X plus K2 G2 of X. So I can have some expected value of some linkage of G1 and G2 and different coefficients on top. But all that happens is essentially this expected value just attaches on to X's. And so it bumps that constant, the K1 and K2, it bumps it outside of the expected value and multiplies the expected value. And then it just attaches on to the functions, the random variables of X. So it's going to look like this: K1 times the expected value of G1 of X plus K2 times the expected value of G2 of X. Okay. So here, expectations, in my mind, they kind of cling or attach to just the random variable of X. Cling or attach to the random variable X. Okay, and bumps constants outside as multipliers. And bumps constants outside as multipliers. Okay, you have probably seen that before, right? But now we're writing it in kind of a different way. And you can tell that I'm just kind of telling you how I think about these, right? And so whatever you need to do to remember that, okay, the expected value, I can actually bring it and I can distribute it into some combination of random variables of X. And then I can talk about the expected value of G1 of X versus the expected value of G2 of X. Those aren't necessarily the same, right? But this expected value, if it's wrapped around some function here, I can distribute it onto anything with a random variable X. Okay. So that's nice. You might remember that the variance doesn't behave the same way, right? And if you didn't talk about the variance before, then we'll see it today, so not to worry. All right. Variance is one of those special expectations that we're going to talk about. And so section 1.9 is called some special expectations. Some special expectations. Okay. So the expected value of X is just, typically we know it as the mean of X. So the expectation values the expectation value E of X is also known as the mean of the probability distribution, as the mean of the probability distribution and written as mu subscript X equals E of X. Sorry, just gonna keeps bumping around here. We've probably seen this before. Usually we just kind of drop the subscript X if it's obvious that the random variable that we're talking about is X. But it's nice to see it there so it's not so scary looking when we see it later on, right? And so here, we can drop this X if the random variable is obvious, right? If it's obvious that you're talking about X, then you can just say that mu is the expected value of X. So the expected value of X is a special case of e to the, or the expected value of X to the power of m. Okay, and that's a special expectation value. So E of X is a special case of the expected value of X to the m, right, where m is 1. Okay. The expected value of X to the m is called the mth moment. Which we call the mth moment of X. Okay. So we can find the expected value of X to the 3, which would be the third moment, the expected value of X to the 4th, which would be the 4th moment, by doing what? Let's say we have a continuous PDF, then we could integrate X to the 4th times f of X dx, for example, right? And then we could find the mth or the 4th moment in that case. Okay, and so we know how to do that, but we're going to go about it just a little bit differently. So there's a related quantity, which is the mth central moment. So a related quantity is the mth central moment right? So e of x to the m is just the mth moment. And so now we're talking about the mth central moment. And we define it as the expected value of x minus mu x to the power of m. The central portion comes from how far is this x from the mean of x. Notice that mu x is the expected value of x, right? And so it's taking the distance of x from the mean to the power of m for that mth central moment. One special central moment is the variance. The second central moment is the variance. So the variance of x, just to develop it a little bit, what we're saying is, okay, if we're saying that this as a fact, the second central moment is the variance, then how can I define the variance? Well, I could define it as the expected value of x minus mu x to the power of 2, right, for the second central moment. So that means that the expected value of x minus mu x to the power of 2 is the variance of x. Okay, kind of doing a crisscross here. The second central moment is this, and it is the variance. Okay. So the second central moment means that we could rewrite the variance as the expected value of x minus mu x squared. Okay. What's interesting is that the variance is not a linear operation anymore. So if I try to distribute the variance, then it's going to have its own properties, right? So constants in a variance aren't just going to be bumped outside. Instead, they're going to be squared. Okay, but I'll show you where that comes from. The variance is not a linear function, right? So the variance itself here is not a linear function. So what that means is I can't just distribute the variance across, some function of x. But I can talk about the expectation value is a linear function, right? So if I can rewrite the variance as this expectation, then I can distribute that expectation. Sometimes that's easier, sometimes it's harder, right? And so the variance is not a linear function or a linear, I should say, operation, sorry. It's not a linear function, and it's not a linear operation either, but using the fact that mu x equals e of x, we can write what? We can write the variance of x is the expectation, and you can leave it as mu if you prefer. I'm actually going to replace it with e of x already. Okay, so a couple of ways that you could go about doing this, but it's the expectation of x minus e of x squared. Okay, just to keep track, because my foiling, I usually have to write it down somewhere, right? But if I do x minus mu times x minus mu, which is technically what I have here, right? If I expand this out, x minus e of x squared, that's x minus e of x times x minus e of x. So then if I go through and I kind of distribute these, then I get x squared minus x mu minus x mu plus mu squared, which becomes x squared minus 2x mu plus mu squared. Okay. So we'll keep that in mind, right? That's really all I'm going to show here. But I like to have it, usually I don't do it in my brain because I don't know, my brain just doesn't foil that well. So I usually just write it down somewhere on scrap paper, just like this. Okay. And so what this becomes is it becomes the expectation of x squared minus 2x times e of x plus e of x squared. Trying to keep it. I wrote too far down here, but that's okay. So then, okay, remembering that e is this kind of linear operation, and it's going to attach to any free values of x, which means it's going to attach to this x squared, and it's going to attach to this x. Thing is, you can find the expected value of x squared, right? And so that's going to be the expectation here, whereas this is just an x. And so if I distribute the expectation, I get the expected value of x squared minus 2 times the expected value of x times the expected value of x plus the expected value of x squared. Notice here that because I rewrote my e of x or my mu as e of x already, then it's obvious that I have e of x times e of x, which is e of x squared. So this becomes the expected value of x squared minus 2 times the expected value of x squared plus the expected value of x squared. This is really negative 2a plus a, that's minus a, right? Negative 1. So really what I have is I have the expected value of x squared minus the expected value of x all squared. And this would be probably the property that we would have used maybe in Stat 230. I don't, because you weren't with me, I don't know what was covered. So, but if anything, then usually this is the formula that you would have used. Okay. So what we're going to say is that if we replace e of x with mu again, right? So, or we could say the variance of x is the expected value of x squared minus mu x squared. Mu x is the first moment, e of x squared is the second moment. So what we could do is we could define the variance of x as the difference in the second and the first moment squared. So the variance of a random variable, and maybe I should just write RV, save us some time, is the second moment minus the square of the first moment, minus the square of the first moment. Just as a reminder, right, the first moment is the expected value of x to the power of 1, which is the expected value of x. Whereas the second moment is the expected value of x squared. All right, so we can talk about the variance in terms of the moments. I'm going to skip a bunch of the work in the next problem, but it is a really good and solid kind of mathematical exercise, not mathematical, but kind of theoretical exercise, developing the remainder of these, what do we call them? Identities, maybe? No. Theorems, I guess. But note that if I take the variance of some combination of constants and random variables, that the variance behaves differently than the expectation value. And so the variance of ax plus b, where a and b are constants, how could I rewrite this in terms of expectations? Well, this is going to be the same as, remember, so ax plus b would take the place of just x, right? So wherever we had x up here, we're going to replace it with ax plus b, but that introduces another ax plus b minus the expected value of ax plus b squared, right? So now I've got kind of a lot going on here, but if you kind of pick your way through it, and I'm going to skip a bunch of steps, but you'll have enough steps to confirm what you're doing, then what you're going to find is that the expectation of, and I'm going to use a bunch of different brackets here, curly brackets, ax plus b, so square brackets around that, minus a mu x, or if you prefer the expected value of x, might be cleaner if you write mu plus b, square bracket, curly bracket squared inside the expectation. This is the definition of the variance, right, as an expectation. Okay. So then if we kind of skip a bunch of steps, what we're going to find is that this is the same as the expectation of ax minus a mu x squared. And again, skipping a few steps here, right? Because I would probably expand that ax minus a mu x squared multiplied by itself. And so here, this becomes the expectation of a squared times x minus mu x squared. But because of properties of expectations, and you know what, I'm going to highlight that skipping steps, right? Just so you don't go back and look at this and go, oh, how does that work? No, you can expand it, but it takes a lot of work in it. There's no point in us doing it, right? Because all I want to get to is this final result, which is that, okay, if I bring this expectation inside, then I can bump this a squared because that's just a constant squared outside. So I get a squared times the expected expectation of x minus mu x squared. But this, remember, is the definition of the variance of x. So that means that the variance of ax plus b becomes a squared times the variance of x. And just to emphasize what happened here, the variance of ax plus b is going to be a squared times the variance of x. How I think of it is that if I need to distribute this variance, right, it wants to hang on to it. We can only find the variance of a random variable. The variance of a constant is 0. However, the variance, right, because a constant is constant, there's no variation there. So that's fine. However, a constant multiplying a random variable, that's going to behave differently once I distribute this variance. And so you've probably maybe used this in the past. And so here we're just looking at how did that come about, right? We can't just go around saying these things. There has to be some reason. And so if I think about distributing the variance, then I need to remember that, okay, how this constant behaves when I bump the variance inside onto the x is it becomes squared. So notice that the variance of b is 0 since b is a constant. Okay. So in my mind, how this variance distributes, and we can distribute the variance by doing this. So the variance of ax plus b is going to be, so this a squared gets bumped outside, right? And so here this variance is attaching itself to this x. So a squared times the variance of x plus the variance of b, which is a squared times the variance of x plus 0, because the variance of a constant is 0. So that's how I get a squared times the variance of x. This is the rule, right? If you distribute the variance onto the x, then you have to square any constants multiplying the x. But how we got there is we leveraged the expectation value definition of the variance, right? So it takes us a lot of work, right? You're going to have to FOIL a bunch of stuff, okay? But then eventually things reduce, and it might be a fun exercise to try, but it doesn't really serve us any purpose here, except we leverage the expectation definition of the variance to do any work with the variance. Okay. Time flies when you're having fun. Okay, so I want to talk about what's called the moment generating function. So the moment generating function is kind of this interesting function, an interesting way to deal with things. And so first we have to develop, what is it? And then what we're going to notice is that sometimes, and more often than not, it's going to be easier to deal with things if we know the moment generating function, as opposed to the individual PDFs, CDFs, PMFs. So the moment generating function which is abbreviated MGF. As we've seen, we could, in theory, calculate all these different moments, right? E of x squared, e of x to the 3, e of x to the 4, e of x to the 5, whatever. So we can calculate each moment of a random variable with an appropriate sum or integral of x to the m. Okay. Of a random variable with an appropriate sum or integral of x to the power of m. But there's this handy trick that's going to take some time to develop, but once we have it and we can use it, then it's going to be powerful. Okay? So the sum or integral of x to the m, but there is a handy trick that lets us effectively calculate them all at once. I say effectively because it's going to require a little bit of work each time, but way less work than integrating each one individually if we're integrating or finding the sum. I actually prefer integration, but we don't get to decide. The function decides. Okay, so that lets us effectively calculate them all at once. We're going to be hinging it. So the way it was developed is it hinges on the Maclaurin series. And so I don't expect you to remember, but I will say recall, let's pretend to recall, oh yeah, the Maclaurin series. Recall the Maclaurin series which says that f of alpha is e to the alpha, which is the sum over m equals 0 to infinity, to infinity of alpha to the power of m over m factorial. So that's something that we're going to leverage here. So if we write the random variable e to the power of tx, okay, so we're considering this x is still the random variable, but we're looking at e to the power of tx. If I rewrite this, right, replacing alpha with t times x, I get t times x to the power of m. That's t to the power of m times x to the power of m, right? And so I can rewrite the summation as the sum from m equals 0 to infinity of t times x to the m over m factorial. And then I can distribute that m from the exponent, and I can say that this is the same as the sum from m equals 0 to infinity of t to the m over m factorial times x to the power of m. Okay. The expectation of this is what we call the moment generating function. And so that's not something that you need to kind of know where it came from, but it is something that we need to know. So the expectation of this is going to be the moment generating function. So then its expectation value defines something called the moment generating function. Defines something called the moment generating function, or the MGF. We're going to denote it by a capital M, a little subscript X, which we will drop if it's obvious again that the random variable that we're concerned with is X, but for now, we'll keep it there. And it's a function of T, okay, which is going to be the expectation of E to the power of Tx. Okay, and so that's a fact. Okay, the MGF is the expectation of E to the Tx, which means what? In terms of the summation, we have the sum m equals 0 to infinity of what do we have here? E to the Tx, T to the M. I must have gotten lazy, so I'm just going to write down what I have here. There must have been a reason. Oh yeah, because the expectation, I can just draw it inside because I have a sum here, and T to the M over M factorial in the end is just going to be a constant. So in theory, I could bump that outside, especially outside of the expectation, and then I can have the expectation of X to the M on the inside. Okay. And so here, I have a blurb about the moment generating function, but I see that I'm very nearly out of time, and it might be a good place to start next day because it introduces the moment generating function a little bit better. So I'll end it there and use that for review. It works out perfectly. If you have any questions, let me know. Otherwise, I'll see you on Thursday. And stop this here.